Well, it's the last day before we go on to a big break. So welcome back, everyone. It's not easy to make it to this class, so I appreciate the folks in class, the people who made it in Zoom as well. On today's class, we're just going to go through section 10.2. We're not going to try to race through it, and we'll try to find a natural stopping point. Good chance we might be able to finish the content in that document there. But before we get going on these problems, any questions whatsoever, folks? Okay, well, let's get started. Section 10.2, it looks like it's a pretty oppressive section at first, but once you practice around with those problems, there's just some small changes on how we did calculus one type of material and how we're now doing it with the parametric curves. They look big though when you look at these things. So this is our first result right here. If you take dy dx with a parametric curve, this formula says you're differentiating y with respect to t in the numerator, x with respect to t in the denominator, and we'll get to the second order derivative and practice that one coming up in the notes. Because this is all new content though, we're going to take these results down here and just walk along down the notes with them as we go, just in case we need to refer to some of these things. So what we did on the first problem up here is we were looking for, let's see, the equation of the tangent line when the parameter is equal to pi over 4. The first step in that process is to just differentiate, find dy dx, because that's the slope at any parameter whatsoever. So like we mentioned, just as a review, we differentiate y with respect to t, throw it in the numerator, differentiate x with respect to t, throw it in the denominator. But to actually get the slope, you have to put in the parameter value, pi over 4, into this result. Leibniz notation looks kind of funny reading that out. The vertical bar you see going this way is the evaluation bar, which says take your derivative, plug in pi over 4, and we got a 0 out of that. Then we plugged in pi over 4 back into the coordinates x and y to actually get the point out. So now we had a point, we had a slope of 0, and we saw that the tangent line had to be just 1. So we'll try a very similar problem coming up next. We'll find for these pair of curves where the tangent line is going to be horizontal and where it'll be vertical. Well, any questions at all, folks, with just a quick review on example 1? Okay, well, let's try this out again. So example 2, this time we're not going for a tangent line equation. We just want to know when is the tangent line horizontal versus when is it vertical. And it's still controlled by this object right here, dy dx. That's the slope at any value where the slope is defined. So we can split this off into two kind of ideas. The horizontal tangent occurs when our derivative, dy dx, is 0. And if you think it back into algebra, vertical lines going this way have undefined slope. So using that as an analogy, we can say we have a vertical tangent when dy dx is undefined. So vertical tangents mean undefined slope. So we're just saying take your derivative, that's all slopes at any parameter value, find out when it comes out to be undefined. But either way we go, whether we're looking into horizontal ones or vertical ones, we still have to calculate dy dx. So that's the superstar in the problem. Let's do it, say, right here. Dy dx by the formula below, looking down right here, says differentiate y with respect to t. So that's just going to be a 2t in the numerator. Then for the denominator, do the corresponding thing, differentiate x with respect to t. We have a 3t squared minus 3. So that gets us started. We're done with that formula for the moment. So horizontal tangent would mean this whole thing goes to 0. If that's 0, that would just mean 2t is 0. So we get a really rapid equation. Solution is just t equals 0. But this is a trickier problem than it looks like because we're dealing with a whole new geometric object, a parametric curve. it doesn't want the parameter value. It asked for specifically points on the curve. We use the parameter value here just to find those points. So we go now to say, we have this occurs at coordinates x, y equals, I think color coding can connect the dots a little bit better. Plug 0 in for this equation for x. So now it's 0 cubed minus 3 by 0. And throw in 0 for this equation over here to get 0 squared minus 3. That gets us a result of 0, negative 3. So our claim is there's only one horizontal tangent on this curve, and it occurs exactly at that point. If you believe it. You know, the best thing about all this is it's really fast to verify. So let's go back to Desmos like we were doing last class. Plug in the equations and see, is that even realistic? We'd want to find out right now if we made a mistake before we just go off to the next thing. So parametric equations start by just going to line 1 in Desmos and putting an ordered pair like this. Set parentheses with a comma, put in the x coordinate, t cubed, minus 3t, y coordinate, t squared minus 3. Then you want to go down here into these values and put in a, put in a b. And now you'll have a slider that you can control where everything goes. So here's how the curve starts to get swept out. As the parameter b increases, something should eventually happen, and there it is. The parametric curve gets swept out in that direction. We said there's a horizontal tangent at coordinates 0, negative 3, and now we could just look. Here we are at 0, negative 3, and that looks very believable. That's a definite horizontal tangent line. So now next we're looking for vertical tangents. And we can see by this curve, there ought to be 2 of them. One right here for vertical tangent line, and one right here. So let's see if we can do the calculus to find out if it fits exactly at those coordinates that we're expecting. So we're halfway done with the problem. Any questions at all, folks, getting that horizontal tangent? Okay, so back to the other side of the problem. We're looking where the vertical tangents would exist. That means the slope, dy dx, is undefined. But dy dx is equal to, let's just put it here to have a quick thing to look at. It's equal to 2t divided by 3t squared minus 3. The only possible way this rational function is undefined is if the denominator goes to 0. So this will immediately imply 3t squared minus 3 is 0. So now we can kind of make an interesting observation. When you're dealing with a horizontal tangent, all you're taking is the numerator and setting it equal to 0. If you're dealing with a vertical tangent, all you're now doing is taking the denominator and setting it equal to 0. I don't know if my color coding fully conveys that, so let me put down some words. For horizontal tangent, set numerator equal to 0, and for vertical tangents, set denominator equal to 0. So it's kind of a cool approach in a way. We're essentially just doing horizontal set to 0, vertical set to 0, and it makes sense. A horizontal line involves y, the numerator. A vertical line involves x equals a number, that's the denominator. And solving this, really rapid, just add 3, divide by 3. T squared is 1. Taking the square roots gives us 2 possibilities, plus or minus the square root of 1, so just plus and minus 1. But like before, these are parameter values. We want the actual points on the curve. And so now we want to say, the moment you find the parameter, don't celebrate too early. We now say this occurs at coordinates xy equals and another xy equals. For the first one, let's plug this in when t equals -1. And for the one below, it'll be plugged in for when t equals a +1. So let's take a look at -1. This is going to turn into -1 plus 3. So it's a +2. -1 here is just a 1 minus 3, so -2. Then rinse and repeat. This time we're plugging in a +1 into those coordinates. So this would be 1 minus 3 for a -2. And 1 minus 3 again for -2 again. So we knew we were coming up with 2 points. Let's see if we have the actual right coordinates though. So we said 2, -2 for a vertical tangent. That does look like it's exactly at 2, -2. Likewise, the other one should be right at coordinates -2, -2, which is matching up with what we put down on paper. So it looks like it's all verified. And you don't have to graph everything when you're doing these kinds of problems. But the reason I'm encouraging it so much is, again, these are a whole new different way to view curves. So you definitely want to play around with the graph as well to try to connect the concepts together. It also makes for a really rapid check. So for the screenshot, I'll put in this left column that describes how to put in the information if you like to use Desmos for your parametric plotting. So here is the screenshot down below. Kind of a big screenshot, and this is the work that supports what we were seeing on the graph. Any questions whatsoever, folks, on that example too? Okay, so this is kind of a tour of a lot of different concepts in Calculus 1, and some of them in Calculus 2. Coming up next is, I think it's concavity. No, we're coming up with a equation of the tangent to the curve at a given point. We'll get to concavity when we get to it. I'm sure it's somewhere in the notes. Yeah, it looks like example 4. So I feel like this one is actually a pretty tricky example. Let's get a whole new page for this one. I made this problem up before I finalized the notes because I realized I assigned something in this assignment here where it's meant to help. So let me open up this assignment. Let's take a look at 10.2. The problems we're about to do are similar to problems 5 and 6. There's a parametric curve provided, parametric equations, and they provide you with some point. We want to find the slope of the tangent line at that indicated point. But this is a trickier problem than it really seems. So on the notes, let's put down just a little quick statement similar to numbers 5 and 6 on the homework. Really, the only difference is I just wrote in the point. I didn't provide the graph. So let's make it extra similar. Let's actually provide the graphs ourselves. This one looks like it's a little bit more interesting as a parametric equation. We have a sine function and a quadratic. So step 1, just put all that information in. I'll move the slider to the left because it is instructive to see how the curve is swept out as the parameter increases. So we'll have sine pi t, comma, t squared plus t. And now, looks like that's all put in correctly. Increase this bottom value. This is like increasing the parameter t. And we get, hopefully, something. There it is. Looks like when it gets to this spot, it stops. And it probably is doubling back. That's why we don't see anything new being traced out as b increases more and more. Probably a feature of the t squared in the problem, causing it to double back. We're interested in the point right here, 0, 2. Let me throw a point on there. I can remember, there it is, how to put a point on it. So 0, 2 would be right here. We want to find out this equation of the tangent line right at that spot. All we know really is it's going to have a negative slope and not too much more beyond it. So let me get a good screenshot of that. And with this screenshot in the problem, this is basically now exactly like exercises 5 and 6. Now that we have an actual graph to look at, just like in those problems. So now we're ready to begin. Well, there's different order that you can do this kind of problem, but I'd say a pretty decent step 1 is just take the derivative, dy dx. The format is differentiate y with respect to t on top, so 2t plus 1. Down below, differentiate x. This will be through the chain rule, pi times cosine pi t. So now that we've got the slope, here's where it gets a little bit vague. We're dealing with a whole new curve, and if we want the slope right here to get the equation of the tangent line, the coordinates 0 and 2 actually don't help us at all, because our derivative depends on the parameter t. So in this problem, we must solve for t as well. We must solve for the parameter t. And the way we solve for it is just kind of unusual because, well, I don't think we've ever kind of really dealt with this sort of outcome in algebra very often, if at all, and definitely not in calculus until section 10.2. The idea is you start at the given point. We have x equals 0 and y equals 2. You use that information to go back to the parametric curve. So from here, x equals 0 implies we have an equation, 0 equals sine of pi t. Then from over here, new equation is that 2 equals t squared plus t. From this point out, we have two equations that we need to check. We're going to solve for a parameter t in one or possibly the other, depending on how you do your algebra. But it's easy to get extraneous solutions on these things. You have to really double check that you really have the right parameter value on both equations simultaneously once you get a solution. So pick your favorite equation and solve it. Let's do the trig equation. That's just a little bit more interesting. We're wondering when sine pi t goes to 0, this could occur if t equals 1, for example, because sine at pi is 0 for sure. This could also be maybe t equals -1, since sine at -1 is also 0, and a whole bunch of other values like t equals 2, t equals -2, and so on. So we can come over here and test these out. Let's just be satisfied with this row and look for more solutions if we need them. I'll put down here, if t equals -1, then back on this equation, I mean, we already know -1 here does balance the equation 0 to 0. Let's check it on this one. 2 would be equal to, that would be a +1 minus 1 for a value of 0. That statement is not correct. We'll never accept that as truth. And so we'll say t cannot be equal to -1. So we have to eliminate this one from our consideration. No guarantee that this one works. And so if we don't get t equals 1, maybe we should just double back and solve this quadratic equation. Let's check out at t equals 1. If t equals 1, then that looks about right. You'd have 2 equals 1 plus 1. I'll put here just a way to say we're keeping t equals 1, that we got 2 equals 1 plus 1 as required. In other words, we were required to find a value of the parameter that balances this equation as well. So we're going to keep this one. T equals 1 solves both. Well, any questions, folks, on finding the value of the parameter to get to that point? Okay, we have to show the algebraic steps finding the value of the parameter, but there's always a huge check. If you plotted the parametric curve, as we have, you can move this parameter down until you get to what you hope is, let's see, the value that we're getting to. Oh, this is a little bit tricky because of the way it seems to double back. At +1, I'm not too sure where I'm at. Let's see if we can visualize it by going this way. Start off at 0, take this one now. Here we go, all the way up to +1. And there we are at 0, 2. So that tells us, yeah, at parameter equals 1, we have the right point. It's a lot trickier on this curve because this curve double backs on itself. So we had to get really creative to find it. Honestly, maybe the algebra is more clear than messing around with Desmos on that one. But once we find t equals 1, solves both equations, we just go back over here. That's the derivative at any parameter value. And now we can say the slope m is dy dx. Evaluate this at the parameter value we found, t equals 1. So now we have 2 by 1 plus 1 in the numerator, divide by cosine of pi times 1 in the denominator. That's a pretty fast expression. We'll have 3 in the numerator. The denominator is, well, cosine of pi is -1, so negative pi. That looks kind of funny. So if you decide to reformat it, usually it's written this way with the negative sign. But in either case, it's still just the slope. So our slope is -3 over pi. We'll use the initial point 0,2 to finally get the tangent line. But this is, to this stage, most of the work so far. Any questions whatsoever to this stage? Okay, so now we can say, just to finalize this problem, the tangent line goes like this. Take y minus the y coordinate from up here, 2. We'll multiply the slope m, which we found to be -3 over pi. Actually, let's just highlight that whole thing. Multiplies x minus the first coordinate 0. That's kind of convenient for us. And so our tangent line equation should be y equals -3 over pi times x plus 2. It's really tricky to be sure that that's the real legitimate equation, unless you're just double checking every single one of these steps that you didn't make any weird small mistake, drop a negative sign, something like that. But if you go back into Desmos, generate out the whole curve again. We showed this last class. You could just throw in another tangent line on top of this and see if it really matches up. So y equals -3 over pi times x. That's a very specific slope. Plus 2 gives us exactly the picture that we want to see. That's a tangent line, because now if we zoom in on this, the parametric curve and the tangent line become essentially identical in a neighborhood right around 2. That tells us we really had the right tangent line. And that's a sensitive process, because if we didn't have pi there, let's say we approximate it to 3.1, there's no way this is ever going to look correct if you zoom in enough. There should be an actual real separation between these two. Let's see if I can indicate that. It looks like it's true, but I'm having to zoom in a little bit further than I would have thought. Let's just make it worse, 3.5. Seemed to come out much worse. The tangent line equation disappeared. So if you have the wrong slope, it's just almost immediately apparent on your graph. I zoomed in way too much. Let me see if I can fix this in a reasonable amount of time. We put it like a accelerator on this mouse wheel. You know, if this ever happens to you, it's not a bad idea to just open a whole new Desmos window. But I think we got back to the original spot. So this is extremely good numerical evidence. We really have all the correct steps down on paper, and that is the true tangent line equation right at that point. Well, any questions at all, folks, on solving that Calc 1 problem? Okay, this problem is, again, pretty unusual. We're giving a pretty big hint. It's similar to exercise 5 and 6, because example 3 feels exactly like example number 1 right here, where we find a tangent line equation. But when you look at it really carefully, it's kind of the opposite of this problem. This problem provided the parameter value, so it was a lot faster to maneuver through. But if you're finding a tangent line where you don't know the parameter, you just know the point of tangency, 0, 2, you have to do this additional work right over here to actually solve for that parameter value. Then the rest of the steps become identical. So we took a look at tangent lines, whether they're horizontal, vertical, or just finding a generic one like this. Next topic is going to be concavity. If we're dealing with concavity, that's where we're going to use this second derivative right over here. So we have a brand new curve, x is t squared minus 4, y is t cubed minus 3t, and we want to know for what values of t is the curve concave up. Deserves a new page. Let's do a bit of a review on this problem right here. In a Calculus 2 class, we don't talk about concavity very often. That was all the way back in chapter 4. We're in chapter 10, just finished chapter 11. So just for a review on this, concave upward means the curve lies above its tangents. If we said concave down, we would say the curve lies below its tangents. So that's a nice part about the problem. The concavity description is just where you're looking for the curve relative to its tangent lines. But that's not satisfying if we're trying to find exactly where it's concave up, exactly where it's concave down. We need calculus. So concave up also means d2y dx2 is positive. So this is the concavity test from calculus 1. And we just so happen to have a formula for the second derivative. I lost it though. Maybe I copied it. Yeah, there it is. So we need to use this formula right here to get that second derivative. So let's start off the process. Step 1 is just to take the first derivative, of course. So it'll be dy dx. Come back over here, differentiate the y coordinate for the numerator. 3t squared minus 3. Then differentiate the x coordinate for the denominator, 2t. Let's highlight that in yellow because now once we go to the second derivative, it's kind of an interesting little format. You redifferentiate this entire thing, and that forms out the numerator. It's going to be a quotient rule in this example for sure. But the denominator we highlighted in yellow stays exactly where it is in position. So here's the second order derivative. d2y dx2 becomes, it says, take the derivative with respect to t of dy dx. For us, that means take this whole thing, differentiate it, 3t squared minus 3 over 2t, and then the denominator is dx dt once again. No need to reinvent the wheel. Whatever you put here goes down below here. So that's the use of this formula here. Any questions with the setup at the moment before we go to crank out that derivative? Okay, let's run through it. And good news is we get to practice again more stuff from Calculus 1. This is the quotient rule coming up. And in the quotient rule, you'll take the derivative of all of this, but place 2t squared down into the denominator. But you're also dividing by 2t, so there's an extra 2t factor. It becomes 2t to the power cubed all said and done. Now, the numerator is going to go together in this kind of way. The way I do this is I differentiate the numerator first and write that as my first factor, just because it's more similar to how the product rule goes. So this will be a 6t when we differentiate the numerator. Multiply by denominator 2t. For quotient rule, we'll put in a minus. Then copy the numerator, 3t squared minus 3. Multiply by the derivative of the denominator, which is times 2. And now this is the result of the quotient rule for just the numerator. And we can start simplifying this way down. We've got, let's see, denominator is 2t cubed. Numerator looks like we have 12t squared. Then from over here, we're distributing in -2 on the left, 2 on the right for minus 6t squared plus 6. Let's double check our work there. 12t squared minus 6t squared. Looks like we've got it. Any questions so far with the algebra to that step? Okay, because we have to solve an honest inequality now, we should simplify this as much as feasibly possible. This turns into, let's see, 6t squared plus 6 over 2t cubed. Then it just keeps on going, so follow the trail of equalities coming down over here now. We could factor out a 6, but I don't know if that would really help us in any kind of way, because this whole numerator is positive no matter what value we put in for t now at this stage. So let's actually leave it just right at that step. I don't think there's any value in doing any factoring here. T squared plus 1 is irreducible over reals. So we're now ready to begin this part of solving the inequality. There's no cut points from when the numerator equals 0, but there is a critical value for when the denominator is 0 itself. That's when the second derivative doesn't even exist. So we have a cut point at t equals 0 coming from this part. That suggests we should break up our interval in this way. So we have two infinitely long regions, one at positive infinity, one going from negative infinity to 0. And on both of these, what we're trying to find is the sign of d2y, dx2. The way we do it at this point, pretty much this is one big algebra review for solving inequalities with rational functions. Once we find all the cut points from setting either the numerator to 0 or the denominator to 0, collecting all the values, you come over here and just grab the most convenient test point. Looks like it'd be a -1. Feed it into the second derivative and take a look at the sign. So d2y dx2 at t equals -1 is going to give us a positive 12 in the numerator. We weren't worried about that changing signs. But the denominator is going to give us a -8. So that means it's negative in this region. And that would tell me I'm expecting positive, so greater than 0 in the other region. It's a good idea to just double check that though. So let's do a little bit more careful work here. Let's click one more test point equals 1. So d2y dx2, evaluate when t equals 1. When you look at this Leibniz notation stuff, it is kind of annoying to write that down. Your hand gets tired after doing it. But if you know you're getting into Calculus 3, Leibniz notation is used a lot. It becomes a really good habit to just get used to writing these things down so that when you see them written down, you know what's being conveyed. So back to this, we're plugging 1 in the numerator. We'll get a 12. 1 in the denominator will give us an 8. So it does come out positive, meeting our expectations. So concave up means the second derivative is positive. The question just asked for what values of t is the curve concave upwards. And now we have a conclusion. The curve is concave up for t bigger than 0. Highlighting in blue just to convey it came from right here. Concave up goes in that direction now for the parameter. We don't know the coordinates where this happens, but we can find them by just sweeping out the parameter, starting at 0 and moving forward. So that's the full process if you're dealing with concavity on these things. It relies critically on this formula right here for the second derivative. Well, any questions at all, folks, on this one? Okay, since we're not trying to race through the problems, let's actually check this one out. I think the check is harder because if you're thinking about concavity through a graph, you have to visualize it through tangent lines. So let's see if this really looks about right. In Desmos, we'll throw in the original curves like before. Let's delete that tangent line. So it starts off with t squared minus 4, then t cubed minus 3t. And let's see here. We want to see what happens with the parameter when it's bigger than 0. That means we need to move the lower value all the way to 0. There we go. Bring this one down to 0. We said it's concave up for parameter bigger than 0. So the curve needs to be above its tangents. Let's write it in. So as the parameter is swept out and we start drawing in tangents, tangents look like this now. The they're kind of hard to draw, and you need to put in a lot of them to really visualize is it above all of its tangents in a region. But even if we put in kind of a trickier tangent, I sort of missed that one, but using your imagination, you can imagine what it would look like. It does look like it's the case. The curve is always above its tangent when the parameter goes from 0 and onward. So that statement down here on the paper does look like it's checking out. Let's throw this on the graph just as an explanation how you can do a check if you decide to do so. And that's finally the full process for concav. We're kind of running out of topics on this, but other topics that you could get into are, let's see, areas under curves, right? You might wonder, what is the area from here to here, this region? Or maybe drop a vertical line at some value and find the area from here to here, not quite a triangle, but would almost look like one. So that'll be our next topic, looking into areas under curves. We'll also look into the length of a curve. And if we have time, maybe even surface area, although I didn't assign that one as a homework question, so I'll ask the class if we're feeling like it for the very last problem on these notes, which is surface area. So it looks like our next question is going to be area under curves. Zoom back into that. I feel like this was
Is there a limit to this? It seems like we could just have layers and layers of functions, right?
no real,
And just keep reapplying the calculus, almost like U substitutions, like just like layers and layers of them, right? And have really complex graphs. Is that the whole concept?
pretty much, yeah. And one thing that's not limited is you can put more and more equations inside there. Desmos is not going to support 3D parametric equations very easily. I think it does do 3D work, but I don't know about parametrics. But mathematically, you could just put in a new function. It's going to really piss off Desmos. Now we're in three-dimensional space. You put in a new function, cosine t. Now it's four-dimensional space. But reality is space-time, 3 dimensions of space and then 1 time dimension. This is actually a pretty important problem. If you're tracking something through space-time now, we'd have to ask the physicists, what would this all represent? It would represent something. But yeah, you're absolutely right. There's really no limit to any of this. In Calculus 3, the change is you're not necessarily dealing with a function like this. Rather, you're going to deal with functions that go like this. F of x equals 3y squared sine x. So you'll have a function that gives you a real number result, but of multiple variables. This is where calculus 3 starts. Eventually, you'll get into functions like, say, r of t equals a vector, where it might be cosine t, sine t. When you get into those functions, very similar to what we're doing here, exactly similar, essentially. But yeah, I agree with you. There's really no limit to this. Even going beyond 4 dimensions, you could start asking questions of what would those parametric curves look like? What are their properties and so on.
Oh, even trying to visualize, I was trying to visualize it as you were adding coordinates, and I was like, whoa, oh, that's tough.
It really is. Yeah. And that's the thing that makes it hard on the Calculus 3 teachers is they need to come up with a way to draw that kind of stuff. So a parametric curve in 3 dimensions, they would try to draw it this way, looks something like this, but to actually convey it's 3-dimensional, that there's a depth to this, really super hard. You'd have to have a handle on shading or find a way to get Desmos, some other computer program to work for you. I think that's what a lot of instructors at Calculus 3 are doing these days, not attempting the drawings, but making like Mathematica or Maple do it for them.
Do the new TI 80 whatevers graph in 3 dimensions, or?
I don't think so. I don't actually own a new TI, so I'm not totally sure. But even say like the TI-84, it can't do parametric curves like this at all, as far as I know. Or I might be wrong about that. I think it might be able to do parametrics. I've never actually done it on the TI though.
I have an HP calculator and it can do 3 dimensional and parametrics.
Well, that's pretty awesome. Some of these calculators are basically just now computers at this point.
When it graphs it, does it look similar to what he just drew on the screen?
Might be able to Control Z that for you.
It can do a lot of stuff. You can make the like Pringle looking like hyperbolic or whatever they are, and you can just do kind of a lot of stuff, but it is in the like 3 dimensions or whatever.
That's pretty awesome. So it's basically a full computer algebra system suite in that calculator day, that HP one.
Yeah, and it's pretty fast too.
Awesome. So yeah, if you really are into this kind of stuff, calculators like that are pretty awesome. But I also encourage you, look into actual desktop applications like, say, for example, Mathematica, or potentially Maple are pretty good options for doing something like on your laptop or actual desktop environment. They just get more and more powerful when you're using those programs. But same kind of idea, the calculator can do just about all that kind of stuff still as well, looks like these days. Well, other questions or comments so far? I should complete this thought right here. If people come back to the notes or have no idea what we're saying, let's say for actual sentence, use Mathematica or Maple applications for rigorous plotting in 3D. Desmos, it can do quite a lot. It does do 3D plotting, but it starts to run into a lot of big limitations. These programs here are really very powerful if you know you're just going to be dealing with lots of math, engineering, that kind of stuff. Well, let's take a look at next, finding areas under curves. This is the formula our author gives us, but I felt like this is really kind of vague how it all comes together. Let's see if we can do a better explanation of what this is trying to say based off the information provided. And I think I typed this out basically verbatim out of the textbook. Our author begins by saying, we know if we have y as a function of x, then the area under the curve from a to b is just integrate f of x. So that was our major calculus 1 thought for integration. It becomes an actual area if f is bigger than or equal to 0. If it's not, we think of it as net area, signed area if it's below the x-axis, positive area if it's above. But this is our new situation. Let's put just a page break here. If the curve is traced out once by these parametric equations, so it can't double back ever, x is f of t, y equals g of t, and the parameter takes on this value, then the area curve, or excuse me, the area integral here, which is this one with y plugged in, becomes that, which is kind of impressive in a way. They say it's done by the substitution rule for definite integrals, but the author doesn't actually show how it goes, so let's see if we can provide the explanation ourselves. It starts off by saying area is the definite integral from a to b of y dx. But then there's a little bit of extra information in the problem. Our curve can be described parametrically this way. So x is f of t, y equals g of t, and they're saying even more with the parameter value. We have alpha less than or equal to t, less than or equal to beta is going to be our new limits of integration from here. So how do we get from that to that? It's kind of vague, but you can already see that you can plug for y, the g of t function. The next big observation is, notice it went from dx to dt. That means there's a differential involved somewhere inside here. And a lot of calculus turns out to be just clever uses of differentials. So if there is a dt in the problem, you could take either one of these equations, probably this one, because we've already used up y equals g of t, and calculate the differential of that. So take the differential. This will give us dx on the left equals the derivative of the function, so f prime of t, and then dt to fill out the differential. So that's now telling us that this whole dx right here turns into that, f prime of t dt. And now we can finally say that the area looks like it really is a definite integral from, last thought, don't forget that the limits of integration have to change. They have to now be with respect to t. So they'll go from alpha to beta. In place of y, we put in the g of t function. And because we use the substitution rule through this differential, dx turns into f prime of t dt. So now the whole integral is represented in terms of t, and that's pretty much how you find areas for any any parametric curve situation like this. It just involves this differential right here, changing the variable to t. This process is actually pretty, again, similar to some things you get into at Calculus 3. You'll eventually do integrals called line integrals, flux integrals, all sorts of weird stuff. But this kind of idea of doing a clever substitution to get an integral of this format is very similar to those Calculus 3 topics. So let's try it out ourselves on example 5. Any questions first, folks, on the derivation?
So this is very close. I feel like we're really just like looping back almost.
Pretty
Right.
much, yeah. This is a huge
I'm sorry if I'm beating a dead horse here, but it feels like we're just looping back to like a plug and play equation.
Yeah, exactly what we're doing, really. Yeah. So we're taking something like this, and instead of just integrating the function f of x, we're just dealing with the parametric equations directly. And the only reason you would ever want to do that is if that function is actually missing. So like in this problem right here, we don't have a clue what y is as a function of x. We could go backwards to section 10.1 and do some really hard work of eliminating the parameter like we were doing in some of these problems. Sometimes it's not very much fun at all. Other times, like in this problem, even if we do eliminate the parameter, we still don't have one function of y. There's two functions there. So yeah, this loops right back to this sort of situation where if we don't want to eliminate the parameter, we're just going to deal with this stuff directly and brute force our integral to have the right values in with respect to t now. But another sense that's looping back is really we're just rehashing Calculus 1 topics over and over again to see how it will go for the new setting of parametric curves.
It's kind of interesting through Calculus 1 and 2. I feel like I'm rediscovering algebra too. Like it's like, oh, we're just adding equations. Every once in a while, like it clicks in my head.
Awesome, yeah. For me, when I was first looking at these parametric equations as a student, it took me a while for it to really click. I had to press the I believe button a few times and just do the problems in the way that it said it had to be done. But yeah, the more you look at it, the more you practice it and connect it back to Calculus 1, it starts to really come together. For example, if you look at this integral just as it stands at face value, that's to me what was really confusing as a student. But if you take away this formula and just view it as, oh, it's a substitution rule, this becomes way more believable. And that's exactly what we're going to be doing in this problem right here. So any other questions or comments before we give it a try? Maybe one question you might have is, if we're going to write down an integral in this format, what is the limits of integration for t? Never specified, is it? But we do have some information. We're trying to find the area enclosed by the x-axis and the curve described this way from x equals 1 to x equals 9. That's a huge heads up on what the parameter value should be, because we could just plug 1 and 9 right inside there and solve for t to get those values. So let's set this up by saying, first, area is a definite integral from 1 to 9. These are values on x now of y dx. But now we have to do a substitution on this whole thing. And the way the substitution goes is we're plugging that in for y. But if you plug that 2t minus t squared in y, second problem that comes up is dx has to go. It has to be a dt instead of a dx if our variables become t. That tells us then what we really need to do next is grab this and calculate its differential. Dx is now going to be 3t squared dt. So that gets us started. But the next thing we always did if we were doing a substitution like this, a u substitution, this is not exactly a u substitution, but it's similar, is we take the limits of integration, x equals 9, x equals 1, and then we always change those limits. That's exactly what this integral is requiring right here. We don't want to undo our substitution after we integrate. So when x is 9, plug that in right here. This will imply 9 is t cubed plus 1. Then from this equation, we have 8 is t cubed. And look how magically the numbers are kind of working out. Cube root of 8 is 2. We take that real number solution, and that should be our upper limit of integration. So 9 goes to 2 on this one. Does that make sense to folks so far on how we're changing these limits? Okay, let's try it again. Because it gave us coordinates or information on the x coordinate, we go back to the x equation up here and write x equals 1. Let me get an actual pen first. Let me try again. When x equals 1, we now have that this implies 1 equals t cubed plus 1. So that would mean 0 is t cubed. And that would mean 0 is now t. So we're replacing 1 to 9, 0 to 2 for our new variable t. So that's a lot of setup, but once you get the hang of it, it's really not too bad to go forward from this point. Area is now a definite integral from 0 to 2. Let's keep those highlighted just to convey how that was substituted in. Throw in y, which is this one, 2t minus t squared. Multiply it by dx. And by dx, we mean the right-hand side of this differential, 3t squared dt. And what we've successfully done is taken a really hard integral where if you're going to really work with just this, you have to eliminate the parameter and actually discover the function of y with respect to x. And it may not be easy to do. There could be multiple functions. You might have to break up the limits of integration and integrate on pieces. Or just do this substitution right here, and now it became a calculus 1 problem right at that step. So let's run through the rest of these steps just to finalize the problem. I think I ran out of space on this one. While we're on page 9, I think it's all those screenshots with the decimal graphs. So to finalize this, we have an area coming out as the definite integral of, distribute through, and we get 6t cubed minus 3t to the power 4 dt. That one should be relatively painless. Antiderivative of 6t cubed should turn into new powers 4. 6/4 becomes 3/2 t to the 4th power. Over here, a little bit easier, you just take negative 3/5 t to the 5th power. This whole expression is evaluated from lower limit 0, upper limit 2. So we have 3/2, 2 to the 4th power, minus 3/5, 2 to the 5th power. Let's put in minus 0 just to make sure we didn't leave off the lower limit of integration. That looks like kind of an annoying computation because of this part right here. So let's make Desmos do some hard work for us. So 3/2 times 16 minus 3/5 times 32 gives us 4.8. Or this is a trick that Bryson showed us the other day. Click on this and you will have 24/5. But they're both exact figures, so up to how you'd like to format your answer. I'll go with the decimal value and say the area is 4.8 units squared. I don't know why I wrote units squared, but if it was a problem with units, we would have said meters squared or something along those lines. We did, folks. That's the area problem on this one. I'll leave it up to the class. Should we double check our work with the Desmos graph, or would you rather just go to the next question?
Next question.
Okay, sounds good. So let's go off to the next. Thanks for the decision on that one. Next one, and this is the last one relative to our homework assignment, is finding the length of a curve. And we actually did this one as a Calculus 2 topic. So now we're reviewing actual Calculus 2. That's kind of helpful for the upcoming exam, final exam. This takes us all the way back to section 8.1. I think we were in the month of September. We did our derivation from scratch and found for taking the length of this curve, you could first turn it into a Riemann sum, use the mean value theorem out of nowhere. But once it becomes this Riemann sum, the answer is this as a definite integral. So this is the length of our curve, either expressed this way in Newton's prime notation, or this way in Leibniz notation. Let's go for that as our expression. So back to the notes, it says the length of the curve should be that. That's kind of an interesting statement, but if you're curious on how it comes to be, here's the thought. If you have a function y that you're dealing with, and you want the length of the curve from, say, let's write a to b, then you would take the square root of 1 plus dy dx, quantity squared, dx. So this is directly imported from section 8.1. So that's the length of our curve. But we'll be faced with situations that look like this. I don't know the function of y. I don't know y as a function of x, rather. These are a function of parameter values t. It may not be too hard to eliminate the parameter on here, but you can imagine these equations could only get worse, right? Where eliminating the parameter is really hard. So let's stick to this as a formula to see how it will go in case the equations are kind of more nasty. So the derivation is kind of clever. It uses the ideas we did before by first putting down x equals f of t, y equals g of t. Here's the first thing that happens. If you're dealing with these two parametric equations, then we actually have a formula for dy dx. It goes dy dx is dy dt over dx dt. That was the first formula that we were working with the most on these notes. So if you square dy dx, you're squaring dy dt in the numerator, the x dt in the denominator. So that's the first thing that's going to happen. Still not a great explanation of where this dx dt squared comes from, because it's sitting down here in the denominator, right? It looks like something is still pretty off. But here's the next thought. These are derivatives with respect to t. And that means this dx also has to change into a dt. We do it through this equation. We're basically just copying the approach for the area formula. Take the differential of that. It'll be like before, dx equals f prime of t dt. I think at this stage is where it gets pretty confusing in the derivation, because when you say differential, dx is now the dependent variable, dt and t over here are independent variables, and this f prime of t, well, you could put that into Leibniz notation as well. It just is kind of strange to look at a differential like this when you impose Leibniz notation. So if x is equal to f of t, then f prime of t is dx dt. So this turns into dx equals dx dt dt. Really kind of weird, but all we've done is change from prime notation here back to Leibniz notation. For the purpose of getting to that spot, we need our dx dt described. So if we take this, well, it's still not exactly what we want. This dx dt has to go inside the square root over here. So we're going to make one extra assumption. If we assume dx dt is positive, and our author makes a comment at this stage. This is a reasonable assumption because our curve has to be swept out exactly once. If you think of the circle where you go and wrap it around multiple times, you're not getting the length of the circle, you're getting double the length of the circle if you wrapped around twice. If we insist that the x-coordinate is always positive, then as you generate the curve, it'll never double back on itself. We will always have that the curve is traversed exactly once. The good news, though, is if you take off this assumption, the author does an even harder approach for the derivation, doing essentially this stuff with parametric curves. So it's not a totally required assumption. It's reasonable, but you can actually weaken it. If you allow this to be the fact, you can go over here and say square root dx dt. We required positivity here, otherwise we would have the formula root x squared is absolute value of x, and absolute value is not going to help us in this problem. So let's put this all together. The length is equal to integrate from new limits of integration, alpha to beta. So here's alpha, here's beta. We have square root 1 plus dy dt squared divided by dx dt squared. Then from this part right here, we go down to this line and put in the differential written as root dx dt squared dt. Now, if you're multiplying two square roots like this, it's pretty forgiving algebraically. You'd get this result. Go from alpha to beta, square root. This distributes inside. When it multiplies here, it just clears out the denominator. And then it multiplies here, giving us dx dt squared plus the denominator is cleared over here, so just dy dt squared dt. So that's one way to derive the formula. There's another derivation. Our author actually gives two for this one. But I like this derivation because it reminds us of a lot of things, like the derivative dy dx right here comes into play, and all sorts of other things. It's the same kind of derivation for area. And when you go to write out the length of the curves, this is actually a pretty forgiving formula. It's not too bad to actually get the lengths. You just, by the derivative of x, square it, derivative of y, square it, square your result, and you're on your way. In a real sense, it turns out these problems here, I think they're actually trickier because you had to really be careful algebraically how you put everything together so you could achieve the cancellation of this square root right here. But not as bad for these problems we're going to take a look into next. Well, we've got like 4 minutes, so we need not get into the very next question. Sorry, I kind of lost track of time there. But when we do come back from the break, we'll go to this problem right here. This is our big application of this section. We're tracking a high energy proton in the Large Hadron Collider. And we have t measured in femtoseconds, distance measured in femtometers. So best attempt at an honest application for parametric curves on example 6. We'll be able to say as we go from 0 to 1 femtoseconds, what is the actual length that this proton traced out? But I don't think we have time to do that just yet. We'll have to review this formula here when we come back, and then we'll finish off these notes moving into section 10.3. It looks like 10.3 is potentially going to be our last section of the course. But any last questions or comments then, folks, before we head on to holiday?
Could you focus a second on what it means by traversing C, or go up a little bit so I can see?
Yeah, this part's right.
Yeah, traverse exactly once as T increases from A to B.
Yeah, absolutely. Let's put down a really quick example to match
Yeah,
that.
I was thinking Desmos might be a good way to visualize it. I was thinking like a function could double back on itself, but in my mind, T could be increasing from A to B, and that could still be happening.
Yeah, so let's try I think the easiest one for this is a circle, basically. And usually when you generate a circle, you're going from 0 to 2 pi. So let's say we go from 0 to 4 pi instead and put in cosine t, sine t. So there's our circle. Let me see what I can do with that. Hang on, I've got a problem with my parameter b here. Add a slider for b. Uh-oh. Oh, there's already a slider for b. I think what I want is 4 pi right here is what we need to put in. And for this, we want to start at 0 exactly. There we go. So 0 on this one. I want this one to be right at 0. Let's see if we can do that. Yeah. Okay. So we're ready to answer that question. We want to find the length of the circle, the unit circle. We know it's just the circumference, right? Just 2 pi. So if we generate out like this, we've gone a distance 2 pi. It's been traversed exactly once, but now nobody can tell it's been traversed multiple times if you did this, unless you're paying really close attention to the parameter value. If we use this same length equation, we're going to find the length is now 4 pi because we went around the circle 2 times altogether. So that's what's being referred to here. If you accidentally have your parameter go from, say, a value that causes the curve to overlap multiple times. Oh, that's the wrong value. Hang on. Then you're not calculating the length of the curve. The length of the curve occurs right at that point, roughly 2 pi. And now going forward, you're just doubling it. There's weirder things that could happen, like you're mentioning doubling back. So it's a kind of a harder example to show, but maybe with this one.
Yeah, or I was thinking like your curve, like you come around and at 4 pi, you would, diverge off and almost like make a figure 8 or something like that.
Yeah, those would be really bad examples too. I think on this one, we have something similar to that where, so we generate this out. See what it does. It goes forward, then stops right there and picks up a value going backwards. And now it's just sweeping backwards and forwards multiple times on this. No way are we getting the actual length of this curve if we integrate from 0 to 4 pi on this one. We'd have to find the actual values that makes it swept out to just once. This is a pretty weird one too, by the way it's actually swept out, all because of the power 2 here, I think. But does that make sense on the issues here?
Yeah, because that one is doubling back on itself, right?
Yeah. Showing
Okay.
cosine's what's causing it. Yeah. Well, any other last questions?
Yeah, that makes sense. Thank you very much.
Yeah, absolutely. Thanks for asking about that one. Well, any last questions at all, folks, so far? Okay, well, won't hold you too longer. Have an excellent Thanksgiving. We'll come back on Monday and find the solution to this problem right here, then move into polar coordinates right after. So take care, folks. If you're working over the holiday, I'm going to be checking my email every early morning, so don't hesitate to write. I'll be happy to help out. And if you're also working problems, don't hesitate to send in any kind of work as well. But we'll come back on December 2nd and finish off the course. Take care, folks. You bet.